Welcome to the course on intelligent product design. Starting from the beginning, we have initially talked about the various processes of design concept generation in our first module, and in this module we are focusing on material selection for mechanical design. And in that, in the last lecture we have talked about the general criteria that we use in terms of selection of the materials. Now, I will just try to recapitulate what we have talked about. That is, we have talked about the 6 very important criteria, that is price and availability of material, and then that whole array of mechanical properties, that is density, modulus, damping, yield strength, tensile strength, hardness, fracture toughness, fatigue strength, thermal fatigue resistance, creep strength, etc. This list is not full, but these are generally the criteria that we use. And then thirdly, we talked about some other non-mechanical properties like thermal, optical, magnetic and electrical properties, which also we have to know before we select a material for a product design. And then every product is going to interact with the environment for which it is designed. So, which means there are chances of oxidation, corrosion, friction, abrasion and wear. So, we have to choose materials such that these these interactions with the nature or these kind of a abrasive force that works on a product because of the natural forces can be minimized. And then of course, when we have to make a product, we have to think of the manufacturing process. So, the ease of manufacture, joining, this becomes an important factor. Finally, it is the appearance, it is the texture, it is the feel of the product that actually tempts us as a customer to buy a product. So, while choosing the material, we have to keep that point also in mind, that what is the aesthetic property of a particular material and how it is matching with the product. So, one by one we will go inside the story. So, first important point is that we have to be aware of the different classes of materials. Like I told you that the very first important class is the metals and the alloys, and there the most important group that is being used for centuries is iron and steels, old hand. Then of course, the ones that are coming up very popular, aluminum and alloys, then copper and alloys, nickel and its alloys, and of course, with the biomedical devices and biomechanical applications, prosthetics, as well as for the spacecrafts, rockets, etc., titanium and alloys. So, this is one major group of materials that we have to consider. The second group that we have to consider, and which is becoming very popular because they are very cheap, inexpensive, and these are the polymers. Polymers like polyethylene, PMMA, which is polymethyl methacrylate, that is PMMA, nylon, polystyrene, polyurethane, polyvinyl chloride, rubbers, polyether ketone and polyether ether ketone. These are some of the very important polymers that are utilized for product design. Just to give you an idea, like this polyether ether ketone is something which is used in terms of space applications, and also in terms of certain materials where for the container, like the Coke bottle, the plastic bottle of Coke, what we know is actually made of polyether ether ketone. They are pretty much actually chemically inert in nature. So, you can use it safely for storing of something. And polymethyl methacrylate, let us take this one, it is also known as perspex. It has a very wide utilization. For example, we choose PMMA for dental fixtures. We also choose polymethyl methacrylate for perspex for different types of transparent system development. polyvinyl chloride, you know it very well that it is used for pipes, and that is something which can take many different shapes. By using certain plasticizers, you can give it different shapes. So, this is a powerful material. So, considering all these things together is our group of polymers. Now, we come to the ceramics and glasses. When we talk about ceramics and glasses, we are not only considering the looking glass, but we are considering all the ceramic materials like alumina, magnesia, silica, silicon carbide, zirconia, cement, etc. So, naturally, they have two different types of use. One is that you can consider them in their fiber form, and then you can make a composite, which we will talk about as the last class of materials. Another is that you can actually use this material like a refractory material. Also, you can utilize this material for tooling purpose. Now, the best thing that they have is they have a very high compressive strength. So, wherever the load is predominantly compressive in nature, you can safely utilize them. The other property, good property that they have is a good abrasion resistance and also chemical corrosion resistance and temperature resistance. So, for this type of applications also ceramics and glasses are very good materials. Now, finally, I come to composites. Composites are always something where each one of them, like let us say metals. What is the strength of a metal? The strength of a metal is that it has high strength, okay, and it has high modulus of elasticity. So, if you need a very stiff product which should not deform, you should use metals. And if you compare that with respect to polymers, what is the strength of polymer? Polymer strength is that it is very, very light. So, metals have the strength and polymers have the lightness. Now, if I can mix these two things together, I can get a composite out of it. Similarly, I told you that ceramics and glasses, they are very good in compressive strength and they are very bad in tensile strength. Metals are very good in terms of the tensile strength. So, if I can mix the metals and the ceramics together, I can get a composite where I can get the good properties of these two things mixing together. So, that is what is the composite, and there are plenty of examples of nature like wood itself or our bone. These are all composites, but also we have our own synthetic composites today like carbon fiber reinforced plastic, glass fiber reinforced plastic or carbon reinforced composite, etc. So, these four groups are the broad classes of materials we have to keep in our mind when we will select materials for mechanical design. Now, when we will talk about the selection process, the first important thing we have to keep in our mind is that like us, that we have many features in our personality. When you write your CV, you put all those features. Like that, every material has certain attributes, we call it attributes. That is the characteristic properties, density, strength, cost, etc. So, design on the other hand, when we are designing a product, it demands a profile. That means, I need such and such density, let us say low density qualitatively, high strength, less expensive, etc. And I need to look into the materials and select all the materials that matches this profile. That is how we will start. And then we will apply the property limits, because you said low density. How low density? Is it between 1000 to 2000 kg per meter cube? If that is so, then immediately steel is ruled out, iron is ruled out. So, that is how we apply the property limits depending on exactly what is the maximum permissible property or minimum permissible property of the system. And so, even if we start with a large group of materials, this will help us to reduce the number of the candidates. There are typical properties that are generally applied are like working temperature, strength, wear resistance, etc. Finally, we will utilize the performance index or material index to further reduce the number to 1 or 2. That is the trick that we will learn today. But before I talk that, I also think of telling you how complex is the selection of material process. Just consider one material which I told you is very popular today is aluminum and its alloys. Now, aluminum and its alloys have actually 7 to 8 series, like let us say 1000 series, one example, which is nothing but pure aluminum, 99% pure. They are ductile and they are generally used as electricity conductor or as foils, the foil that we utilize as aluminum foil. On the other hand, the 2000 series aluminum, which has a percentage of copper mixed with it, it is strong, much more stronger than pure aluminum, and it is used in aircraft skin, rivets, etc. If you go for 3000 series, that is generally come up with the mixing of manganese. Manganese gives you a corrosion resistance. So, it is used for roofing sheet, cooking pan, etc. If you go for 5000 series, that is aluminum plus magnesium, magnesium gives it again strength much more than copper. So, it is used in pressure vessels. Then if you go for 6000 series, you get not only aluminum and magnesium, but also silicon. So, it is used as a stronger applications like window frame, edge hardened products, etc. 7000 series again give you strength, edge hardening and all these things together. So, that is with the zinc, and also we have a variety of aluminum with lithium alloys, which is strong, very light, and it is generally used in aircraft skin. Now, in addition to these 1000, 2000, 3000 series, you will also see another subscript called O or H in aluminum. O means it is annealed and H means it is strain hardened. So, let us say that I have to choose a particular variety of aluminum for automobiles. Okay? We know that light automobile is something that we always look for. So, how do we choose it? Well, first of all, I choose a material because it is a product. Then which family I have to choose? Ceramics, glasses, metals, polymers, elastomers, composite. Property limit we are going to apply, and then we will naturally see that the strength requirement and all these things will keep the metals and the composites as two candidates, but composites till today, other than the aircrafts, application of composite for automobile is very expensive. So, except certain parts of a racing car, we normally do not go for the composites. So, we will keep ourselves in the metallic domain, and as we are looking for a lighter density, lighter automobile. So, out of all the possibilities of the classes of metals, we would be ready to take aluminum alloys. Now, as I just now told you that aluminum has all these varieties in it. The variety that we will go for is the 5000 variety. Why? Because it is the 5000 variety which can be used in terms of a thinner skin and also better in terms of corrosional properties, and it has a good strength. So, it is light, it has good strength, it has corrosion resistance, and you can also form it to, you can give different complex shape to it. So, the sheet metal bending and all these things you should be able to do. So, in spite of available of all of them, we will go for 5000 series. Now, 5000 series does not end there. 5000 series has many varieties, but we will go for typically 5083 series, and which also is to be strain hardened. So, strain hardening itself, you can see 5083 has many varieties, but the best variety of strain hardening is H111. So, that is the complex process today, that in terms of the choice of the material, this becomes the final choice. So, this is just to tell you that considering all these attributes that I have given here, one can come into conclusion that for automobiles, one of the best choice is 5083 H111. Now, let us see that what is the process by which we can do this entire thing in a very rational manner? Well, first important thing is that whenever we will design any structural element for product, it will involve minimization or maximization of an index, and this index property are functions of three things: f is the functional requirement, g is the geometric requirement, and m is the material requirement. And for certain designs, luckily, not for all designs, towards the end I will show you how you can get these things coupled. But for certain designs, luckily the separation exists. That means you can consider the functional properties separately, geometric properties separately, and material property index separately. Now, for material choice, we will go for this material index specifically. So, let us see how we can do that further. I will first give you a very simple example. The example is for a light stiff tie. What is a light stiff tie? Well, what is a tie? Tie is not the same tie that we put in a knot. Okay? In the terms of a structural engineer, a tie member is something which is always designed to carry the tensile load. Okay? So, there is tensile force, right. So, if I take this member and make sure that I am only pulling it always, then this becomes a tie member. So, let us say I am trying to see a tie member, but it has to be stiff. What does that mean as stiff? It means it must have a very high modulus of elasticity, and also it has to be light. That means it must have a very low density. So, that is what we are looking for. Okay. So, what is the mass of the tie? M is area of cross section, length and density, product of the three, right. So, we need to minimize this mass. That is what is my performance index, right. In order to get a light stiff tie, we need to minimize the mass. Now, what is the deflection of the tie? Well, I am not going to the details of structural engineering, but you can get it as a ready-made formula that the deflection, like let us say if I apply a force T, then the deflection that it will increase, okay, by its size, and let us say that these increase in any side. So, suppose if I close it in one side and this is delta, then this delta is nothing but T L over A E, or here if I consider T as F, then it is F L over A E. So, F L over A E is delta, and that is the deflection, and that deflection has to be lower than a certain given deflection, then only it will be stiff. A rubber band is not stiff enough because it deforms a lot. Okay. Now, I know this much, fine. So, now I am looking at that what is then my mass? Well, in my mass we have area of cross section, we have length, we have density. Length of a tie cannot be changed because of it is connecting between two members. Density we are looking for. So, it is the area only which is the free variable, that is very important. So, that means area from this particular relationship can be written as what? M by L rho. Area is that free variable. Now, I also know that delta is given to us. So, delta is what? T L by A, and delta is fixed for us. So, what is the area then in terms of delta? It is nothing but T L by E delta. So, now if I actually write it here in this relationship, then what I am going to get? I am going to get T L by E delta would become equal to M by rho L rho, right, M by L rho. Okay. So, I can write this in a manner now that what is the mass now? The mass is now T L square rho by E delta, right. And I can write this in terms of three different sets. This T by delta, okay. So, this T by delta is something that we can consider separately. So, T by delta. So, this is mass is, you can see it here as T E delta. So, this is delta, okay, this is delta. So, we can write that T by delta as one group, that is the functional group, and then we can write this L square as the geometry group, and then we can write rho over E as the last group, which is the material property group. So, if I have to minimize the mass, what does that mean? It means I have to minimize the rho over E, and that actually means that you have to maximize E by rho, because maximization of E by rho is the same as minimization of rho by E. So, this example tells us that how to figure out that what will be the material property index. In this case, it is M is E over rho. Now, this provided you consider area as the free variable. Okay. Now, for a beam which can actually take bending moment, not a tie, this would become square root of E by rho. For if you consider height only as a free variable, it will become e to the power of 1/3 over rho. If you consider width, it will become E by rho. And similarly, from the strength point of view, a material property index is sigma f 3 by 2 divided by rho. And if I consider a column member, then it is CMAL rho, and material property index correspondingly is square root of E over Cm rho. So, you can actually find out similar material property index corresponding to every application, and we can actually use a book which is Aspie's book, material selection for mechanical design, very effectively. Okay. Even if we do not have all the ideas of mechanical engineering, still we can use this effectively, material selection for mechanical design. There is also a software that is available, but even otherwise the book itself is very, very helpful. Now, let us take some case studies. First case study is related to our aluminum alloy vehicle body material selection. Okay. Let us look into this case study. By the way, this is one of the designs that our students developed for automobiles which can be parked one against the other. Now, one important thing in automobile design we have to keep in mind is that way long ago in 1975, there is a CAFE regulation that actually restricts the fuel emission from the obnoxious emissions pollution point of view from 14 mpg to 28 mpg between 74 to 87, and the CAFE limit remains 27.5. So, every automobile is to be designed in that manner such that you have to have a good powertrain for efficient power transmission. You have to select the material of the car body such that it is lightweight, such as aluminum alloy, most efficient design such as you carry out some structural optimization, fuels with less noxious exhaust. Okay. And also there was a shift to make actually smaller cars. So, that is how the fuel economy had been achieved. Now, if I look at these from a material index point of view, let us take a flat panel. Okay. If I take a circular panel, then I can write this as the mass pi a square t rho, okay, where 2a is the diameter of the panel, 2a is the diameter. Now, this area, I mean, through some manufacturing process, we can also get these in terms of the width and the length of the panel, like LL and LT. So, this is the transverse and the longitudinal geometric shape of the panel. So, you can write the area in the same manner, and then you can get the mass which we have already discussed. Similarly, you can get the mass of the panel. The question now will be, what is the deflection? This is why we had chosen a circular panel for which a nice closed form relationship exists that gives us the deflection with respect to the force. Now, LT and LL, the size of the panel is actually fixed. So, I can express the only free variable thickness, and I can express thickness in terms of all the other parameters. And if I express thickness in terms of all the other parameters, then I can rewrite the mass of the system. And then exactly what we have done for that simple timer case, I can divide this entire thing into 3 parts, out of which this part is functional. We already know this is functional, this is geometry, and this is the material property index or M, which is what in this case? It is not E by rho, or it is not square root of E by rho, but it is E to the power 1/3 over rho. Okay. So, that means in order to minimize the mass, you have to minimize this rho over E to the power 1/3, which is equivalent to maximizing E to the power 1/3 over rho. That is the way we generally keep the density in the denominator. This is just a matter of convention. So, this is the way you need to minimize. Now, if I look at all the typical materials that we can utilize for car making, steel, concrete, aluminum, all of them, and check their E to the power 1/3 over rho, first thing you will see that CFRP is the best, and no wonder, that is why it is used for racing cars, I told you, but it is very, very expensive. So, what is the next best? Well, next best, if I look at it, GFR wood is there, but wood today is not utilized at all. PU also has other problems, so you can cross this. Wood is not good for mass manufacturing point of view. So, glass, no, it is bad in terms of compressive strength, okay, bad in compression. So, it is, we cannot utilize it. Now, we can see that aluminum and steel are the 2 competents, and out of this aluminum is a better choice. In fact, we can actually get a Ashby chart like this, and in this chart right now we are looking at only, Ashby chart can be multi-dimensional. I have only shown you here the 3 part of it, that is E versus density, and with E to the power 1/3 over rho, which will be some kind of a slope on this line, you should be able to see what are the materials in which you get a low density, on the other hand you get a high modulus, and you will see composite is always one group, and some parts of the metallic alloys also work there very well. So, similar to these E versus density, you can also have a strength versus density. Okay. If that becomes your important criteria, you can also have E versus strength, if that becomes your most important thing to decide the fate of the material. Now, let us quickly look into another example. This is the example of a flywheel. You know, flywheels are utilized for storage of kinetic energy. So, flywheels are like electromechanical batteries for us. So, store energy in a rotating mass. So, motor connected to flywheel will create a start rotor the spinning, that is, we can say it as if it is charging, and when that it is spinning and then the wind has picked up, then it will turn the motor, and that is the discharging part of it. So, now let us say I need a material that can store most energy, that is kinetic energy per unit mass. So, what is the kinetic energy? I can find out the kinetic energy similar to half mv square, it is half I omega square, and then I can find out the expression of it. And then what is the kinetic energy per unit mass for a circular system? I can find it out, which will become half omega square r square. Okay. Now, we have constraint here. What are the constraints? That a flywheel cannot arbitrarily rotate at a very high speed, because you can see here that in order to have better efficiency, the omega can be increased, but then it is going to disintegrate. Okay. Cost should be within reason, and the fracture toughness should be adequate, Gc should be adequate. So, if it is only U by M that I need to figure out, and then if the strength is the only criteria, it would become half sigma f over rho as one of the criteria, but we have the fracture toughness as our concern, and that is related to the stress intensity, and this is the expression of the strain energy release rate Gc, which we are going to use in terms of measuring the fracture toughness. So, Gc can be, by using these last two equations, can be expressed in terms of Kic as one of the property in the mode 1 fracture and KIC square over E, and which has to be greater than 1 kilojoule per square meter. That is what is our requirement, that is the property level. So, what are the subsets we can consider? Foams, polymers, wood, composite and alloy. That is what from the 1 kilojoule per meter square. Now, you can actually do all these KICs, and then from this KIC list you can try to figure out KIC square over E. I have just given KIC, and then this is the KIC over E, and you can see if you have to maximize KIC over E, that means maximize KIC and minimize E, then you have to come somewhere in this region. This is the best region. That is why polymers come as very good candidates in this region. Now, let us look into that our criteria after applying this is sigma f over rho. From the selection point of view, again wood, composite, aluminum alloy, titanium alloy and steel would come in our active set. So, you can have a sigma f over rho plot, and you can see the maximum of sigma f over rho, that is minimum rho, and maximum sigma f will again come here, engineering composites, and all our choices are above this limit actually. Okay. So, we have all these limits with us, using which we can actually choose the material. So, this is where we will close our discussion today. In the next class, we will take one more example of how to select the material for any other applications. We will do some case study, so that you will be able to know that for different cases how you can select the material. Thank you.